Hello everyone. Let me begin with a little curiosity. Have you ever noticed how a swimmer underwater can look up and see the world outside through a circular window, almost like a shining patch of sky? Beyond that circle, everything appears dark. This fascinating phenomenon is linked to what we call the critical angle. The critical angle is simply the angle of incidence in a denser medium, like glass or water, for which the angle of refraction in the rarer medium, usually air, becomes 90 degrees. That means the refracted ray just skims along the boundary of the two media. And why is this important? Because once we understand this condition, we can explain one of the most magical effects in optics, total internal reflection. The foundation of optical fibers, sparkling diamonds, and periscopes all lie here. As you can see in the diagram, the incident ray bends, and finally, at this special angle, the refracted ray travels along the surface. That angle is our critical angle. Let's go step by step into the math behind this. We begin with Snell's law, which tells us refractive index of the first medium multiplied by sine of the angle of incidence equals refractive index of the second medium multiplied by sine of the angle of refraction. Mathematically, we write μ1 sin I equals μ2 sin R. Now, imagine light traveling from glass into air. For glass, we take μg. For air, we consider μ equals 1. At the critical angle, the angle of incidence, I, equals C, and the angle of refraction, R, equals 90 degrees. Substituting these values into Snell's law, we get μg sin C equals μ a sin 90 degrees. But we know that sin 90 degrees is equal to 1. So the equation becomes μg multiplied by sin C equals 1. Therefore, μg equals 1 divided by sin C. And in another form, μg equals cosecant C. This shows that the refractive index of the medium is equal to the cosecant of its critical angle, a neat relation that directly connects the two quantities. Let's test this relation with some examples. First, consider glass. If the refractive index of glass is 3 by 2, then from the formula, sin C equals 1 divided by μg, that is, sin C equals to by 3. So the critical angle, C, is about 42 degrees. Now for water. Its refractive index is 4 by 3. So we write sin C equals 1 divided by μw, that is, sin C equals 3 by 4. This gives a critical angle of roughly 49 degrees. Notice the trend. The higher the refractive index, the smaller the critical angle. And here's a fascinating application, diamonds. A diamond has a refractive index of about 2.42. So we calculate sin C equals 1 divided by 2.42. That comes to approximately 0.413. Taking the inverse sign, we find the critical angle C is just 25 degrees. That's why diamonds sparkle so brilliantly. Light entering the diamond gets trapped inside due to repeated internal reflections before it finally escapes. To make it clearer, let's look at a small table of examples. Water, refractive index equals 1.33. Its critical angle comes out to be about 49 degrees. Glass, refractive index equals 1.5. That gives a critical angle of about 42 degrees. Flint glass, which is slightly denser, has refractive index 1.57. Its critical angle is around 39 degrees. And finally, diamond, refractive index equals 2.42. Here the critical angle is very small, only about 25 degrees. So we can conclude, as the refractive index of a material increases, the critical angle decreases. That's why optically denser materials can trap light more effectively, and in the case of a diamond, produce that brilliant sparkle due to repeated internal reflections. Now here's something even more exciting. Does the color of light affect the critical angle? The answer is yes. Remember that the refractive index of a medium is not the same for all wavelengths. Shorter wavelengths, like violet light, are refracted more strongly, which means they have a higher refractive index. Longer wavelengths, like red light, have a lower refractive index. So what does that mean for the critical angle? Since mu equals 1 over sin c, higher mu means smaller c. Therefore, violet light has the smallest critical angle, while red light has the largest. In other words, the critical angle increases with the wavelength of light, smallest for violet, largest for red. Another subtle factor that affects the critical angle is temperature. When you increase the temperature of a medium, its density decreases. That in turn slightly reduces its refractive index. Now recall our relation mu equals 1 over sin c. So, if mu decreases, that means the denominator gets smaller and therefore sin c becomes larger. A larger sin c corresponds to a larger critical angle. In simple terms, as temperature rises, the critical angle increases. For example, a heated piece of glass will have a slightly higher critical angle than the same glass kept at room temperature. This is why precise optical experiments often need careful temperature control. Even a small change can subtly affect the way light behaves inside the material. So let's connect everything we've learned today. We derived the key formula, refractive index equals 1 divided by sine of the critical angle, or cosec c. We saw that materials with higher refractive index have smaller critical angles. We also discovered that the critical angle depends on wavelength, smallest for violet, largest for red, and it increases with temperature. And most importantly, this concept explains real-life applications all around us. From the sparkle of diamonds to the working of prisms, from endoscopes in medicine to the internet carrying optical fibers that connect our world, all rely on this beautiful relationship. I hope this makes you see optics not just as equations but as a gateway to understanding technology and nature. In our next session, we'll dive deeper into total internal reflection and explore how it shapes modern inventions. Until then, keep your curiosity shining.